Recording the talk. Yes, we have been permission to at least record the talk, so that is now being done. Okay, so I will now turn the floor over to Deanna Needell, one of our co-organizers, to introduce the speaker.
Thanks, Mark, and all the other organizers for organizing this, and especially to our esteemed speaker, Andrea Bertozzi, who will be our first speaker today. And I have a very long bio, which I've trimmed because she has so many amazing accolades. So Andrea Bertozzi is an applied mathematician with expertise in nonlinear partial differential equations and fluid dynamics, although that's very, very broad. She does everything. She also works in areas of geometric methods, image processing, crime modeling and analysis, swarming, cooperative dynamics. You'll see today she's been working on COVID-19 research. She completed all of her degrees in mathematics at Princeton. She was on the faculty at Duke from 1995 to 2004. She joined UCLA in 2003 as professor of mathematics. And since 2005, she has served as director of applied mathematics, overseeing the graduate and undergraduate research training programs at UCLA. In 2012, she was appointed the Betsy Wood Knapp Chair for Innovation and Creativity. Her list of honors is way too long for me to include everything here, but she has many accolades, including the Sloan Research Fellowship, the Presidential Early Career Awards for Scientists and Engineers, Kolevsky Prize in 2009 from SIAM. She was elected to the American Academy of Arts and Sciences in 2010, to the Fellows of the Society of Industrial and Applied Mathematics, SIAM, in 2010 as well. She became a Fellow of the American Mathematical Society in 2013, a Fellow of the American Physical Society in 2016, and in 2018 was elected to the U.S. National Academy of Sciences. In July 2019, very recently, she was awarded the SIAM's Kleinman Prize, which recognizes contributions that bridge the gap between high-level mathematics and engineering problems. This award is based on the quality and the impact of the mathematics. So she has graduated many PhD students. I think she has counted 37 and has mentored over 40 postdoctoral scholars. So it is my greatest pleasure to introduce our speaker, Andrea Bertozzi. Thanks very much.
Thanks, Deanna. It's a real pleasure to be here. I'm sorry that we're doing this because of a pandemic, but it's also nice to see the community brought together. So I'm going to start the talk. I recognized that COVID-19 was going to be a problem. Back in I think we all sort of realized in January it was likely to get to the US. I don't think we quite understood the impact that it was going to have. I started thinking about this problem from a research perspective in February, and now I find myself spending a good portion of every day working on it, not exclusively, but nevertheless, it's something that I've gotten interested in. So what I'm going to do today is I'm going to give everyone my viewpoint of what the challenges are, and also kind of go over some of the basics of epidemic modeling, because prior to this pandemic, epidemic modeling was, it's a well-developed field, but it lived pretty much within epidemiology, whereas now, I think with the advent of machine learning and also the fact that it's affecting so many of our lives, we see people from a number of different fields getting interested in it, collaborating with people in epidemiology and medicine. And I think there are some really interesting research problems here. So let's see. All right, so I'd like to dedicate this talk to my two sisters who are also very much involved with the pandemic. My youngest sister, Diana, is an occupational therapist at a New Jersey nursing home. We're all really relieved to know that she's now a survivor of COVID-19. She had a mild case, and she's currently treating patients in the COVID ward where she works. You can see the the costume that she has to wear every day when she's working at her nursing home. My sister Carolyn is a chemical biologist at Stanford, an expert on carbohydrate chemistry, and her lab is currently involved in some work on the virus. So I have to say that I think I have the easy job compared to my two sisters. They're really my heroes. Okay, so now let's talk about COVID-19 and epidemic modeling. So I'm going to talk about this both from the perspective of how it's impacting the world and also from the perspective of mathematics and modeling. So prior to our shutdown here, there was a study done at Imperial College. They have a group of experts in epidemiology. And this report used a model that was previously developed for an influenza pandemic, but it was able to be adapted to COVID-19. And what this model did was it said, hey, let's look at what could happen if countries, in particular Great Britain and the US, do absolutely nothing in terms of distancing. Everyone goes about their lives, business as usual. And what this model did was it predicted a huge number of deaths could happen. So they were looking at over 2 million deaths in the US and over 500,000 deaths in Great Britain. And you can see the curves of the death curves that they were predicting. This report that came out on March 16th had a profound impact on policies in both the United States and in Great Britain. And you all know what happened. I mean, we're now right of that incident. So we're all now, basically shut down. Only essential workers are still going out and working. Of course, people have to do some work because otherwise we have no food. Otherwise, people who have medical emergencies won't be treated. And so there is a need for some people to work. And those of us who can work from home, of course, are doing that. And there's quite a lot of people working from home. But this has made a huge impact on all of our lives. One of the interesting features of COVID-19 is the percentage of the population in different age groups who are affected at a level that require hospitalization and medical intervention. And so these are some data points from the Imperial College report. And one of the takeaways here, of course, everyone knows this at this point, is that very young people really are rather unaffected, statistically by this disease. But the older you get, and it's a monotonic increase, the more likely you are to require hospitalization, the death rates go up. And this is something that's a little different from a lot of the influenzas that we've looked at. Influenzas can often affect young people, especially babies and young children, quite significantly, whereas we don't see this so much for COVID-19. All right, so I started corresponding once we were all shut down. I started corresponding with some of my friends over Facebook. And one person in particular, Elisa Franco at UCLA, was posting these graphs almost every day. She's from Italy, and she was looking at all of the Europe data and measuring the exponential growth. So one of the things you see with a pandemic is at early times you have exponential growth in the number of new cases and in the deaths. And so one might ask, why does this happen? It happens because of a very simple process. In order to become infected with the disease, you have to come into contact with somebody else who's infected, or you have to come into contact with, say, an object that has recently been infected by the virus. But typically it involves close contact between individuals. And that's a very simple mechanical rule. And that simple mechanical rule leads to early time exponential growth. right? So we can see this. So if you haven't already done this, a lot of people have done this. You can literally take the curves in time and you can put them on a log linear plot, and you should see the curves kind of having sort of you can do linear fits to these curves. So in terms of what people are measuring, if you go online and look at some of the data that's up there, so for example, the New York Times has a great website with data. One of the things they look at is doubling time. So that's the time it takes for the number of infections to double. And when you see that doubling that happens over a span of 2 to 4 days, that's kind of scary, right? Because then the numbers are just going to go up and up and up and skyrocket, right? So this is something that happens at early times. And of course, it's a reason why we need to shut down. But that's not the only thing that happens when you have an epidemic. So one of the things I'm going to get to is the issue of herd immunity and how the idea of having a sufficiently large fraction of the population actually leads to a decrease in the number of cases. One of the things, though, that you can do is look at the exponential growth rate, and you can compare it to rate constants for the disease. So the rate constants that are the most important are the transmission rate and the recovery rate. And there is a dimensionless number called the reproduction number R0, and it's the ratio of the transmission rate over the recovery rate. And so one can actually phrase this exponential growth process in terms of that variable dimensionless number R0. So this is a fairly simple calculus exercise that can be done. So now, what happens once you have quite a lot of people infected? So if we were to have our society go on as normal and just let the disease spread rapidly through the society, then we need to start looking at not only the number of infected people versus the susceptible people, but we also need to look at the recovered people as well. Because if everybody's had the disease and has recovered and is immune, then you're not going to have more infections because nobody can acquire the disease. So the simplest model that explains this kind of dynamics is called the SEIR model. It stands for susceptible, infectious, recovered. It's what we call a compartmental model. So what you do is you take your population and you decompose it into compartments. So basically everybody has to be in one of the 3 compartments, and then there is a rate of transmission or movement from one compartment to the next. So it goes directly from susceptible to infectious. And this transmission has our rate beta, the transmission rate, which has units of 1 over time. And that is multiplied by the susceptible number times the infectious number. And that formula basically captures this dynamic that I mentioned, which is the dynamic where we require an infected person to come into contact with a susceptible person with some rate constant beta that allows us to see those susceptible people move to the infectious category. Then we have another process by which people who are infectious recover, and that happens with a recovery rate gamma. And so we can put all of this together and we get a coupled set of ordinary differential equations. So I'm showing those here. So here are the 3 ordinary differential equations. There's this important R0 dimensionless number. It's the reproduction number. So one can actually rescale these equations and rescale the initial data so that the whole dynamics can be put in dimensionless form. And what we see over here in this plot on the right is an example. This is taken off the Wikipedia page for compartmental models. what we see is a plot of what this dynamic looks like over time. So you start at time 0 with almost everybody in the population is susceptible, but a small number of infecteds. The infecteds are shown in green, and nobody's recovered at time 0. And then you let the epidemic evolve. So you evolve according to these differential equations. And so what you see is that at early times, on the green curve, that the infectious numbers are going up. And in early times, that's exponential growth. But as you go into the epidemic, at some point you level off and you hit a peak. And then you start to decay, and then you asymptote to some values as time goes on. So as we go to the very end of the epidemic, you might think naively that you end up with everybody in the entire population recovered. And that's actually not the case. The percent of people who are recovered at the very end versus the percent who are still susceptible, that number is determined by one parameter in this model, which is R0, the dimensionless reproduction number. So you'll always have some fraction of the population still susceptible, and you'll have a fraction that's recovered. Okay, so, all right, so one of the other things about this model is you can easily see that if you add up the 3 equations, that the time rate of change of S, I, and R, the sum of those things is 0. So that's just a conservation law. Okay, so that's a simple thing that we can do. So if we solve for 2 of these quantities, then we know the third quantity immediately because they sum to the total population. Okay, so here's another thing we can do. If we want to figure out from any initial conditions what the final state of the epidemic is, there's actually an exact formula for that, for SEIR. And it's a very simple thing you do. What you do is you take the S equation and you take the R equation and you divide one by the other. And you actually remove the I, the infectious part, from this equation. So you end up with a differential equation for dSdR in terms of S and R, and you can solve that exactly. So this is what the solution looks like. It's just an exponential for S in terms of R. That allows us to also get a formula for S infinity and R infinity. Those are the asymptotic values as we take time to infinity. There's an exact formula. It's in terms of the Lambert W function. So this shows that at the end of an epidemic, unless you start with S0 equals 0, meaning that you have no susceptibles at the beginning, which is kind of a silly initial condition, not all of the individuals of the population will have recovered, so some remain susceptible.
So Andrea, I have a question here about whether these models can be changed to allow for the total population to vary over time if the epidemic takes a while to progress.
Sure, yeah, so in fact I'm going to show that. That's a good question. I'm going to show that in an upcoming slide. So that's a really good question. Okay, so now what I want to do is I want to talk about this whole idea of herd immunity and how we understand that. So I like this graphic. This came from a paper that I'm going to talk about in a bit by Bootsma and Ferguson, published in PNAS in 2007. And so what they do is they compare the proportion of the infected versus R0 for 2 different scenarios. So one thing that we know is that there is a minimum fraction of the population that you need for herd immunity. And that's basically 1 over R0. And you can see that that's a formula that you can derive very easily. You can go back to the original equations here, and you can look at the I equation, and you can ask, is there an obvious condition for which dIdt is going to be negative, right? And that's a simple calculation you can do, and you get a formula for the number of susceptibles, right? And it's just S over N has to be equal to, that's percentage, susceptible has to be equal to 1 over R0. And so if you then take that and subtract that from 1 to get the recovered population, then you get this red curve right here on this plot on the left for this. So for example, if you take R naught equals 2, then what we see is that if we somehow can magically snap our fingers and have half the population immune, and of course having a vaccine would allow us to, a widely available vaccine would allow us to do that, then that gets us to the red curve. Now there's another curve here, which is the blue curve. What is that? That curve is what you get at the infinite time if you let your epidemic run uncontrolled through the population, and it's a bigger number than what we have for the minimal percentage needed to have herd immunity. And so we can then look at different scenarios using these two curves, and they have this example on the right. And so they look at the case of R naught equals 2, and they say, okay, let's let that run through our population with no controls. And you get the green curve here. So you have a huge spike in cases after, I don't know, a little over a month. And then you very quickly decay to almost everyone in the, not everyone, but I guess 80% of your population will have acquired the disease. Now, another option that you have is to introduce some kind of controls to your population, which removes some of the connections between people, and so the transmission rate is cut down. And so there's an optimal way to, if you can do that, to get only 50% of the population infected, that's your blue curve. When that dies down, then the disease will go away. But if you actually push it down too far, which is the red curve, and then you remove the controls too early, you're going to see it bounce back up again. So you'll see a second wave, right? And there are people talking about this in the news right now, whether we're going to see a second wave, right? So I'm going to stop here. Are there any more questions?
Paulina Zelanovic, who I guess you might know from around.
I do. Hi,
Yep.
Paulina.
She wanted to know whether the recovered population also included those who died from the disease.
Yeah, we're not looking at deaths here, but absolutely, if you have a death rate, then the death rate will be a fraction of your recovered, your quote unquote recovered population, right? And of course, dead people in theory are not going to transmit the disease either, at least, you know, under the right conditions. So, okay, so that's a good question. And there are, by the way, this is the absolute simplest model you can write down that has the recovery in the model, but I'm going to show in some more slides some models that are a little more sophisticated than this one. But it gives you the idea of what happens, what's the basic dynamics of an epidemic, why do we get this rapid growth, why do we have peaks, and then why can we get second waves under controls. So here's another graphic of what I was referring to about this, you know, where the peak happens. So you can also look at phase planes, right? This is something that people look at in dynamical systems all the time. And so this is a phase plane where we plot the susceptible versus the infecteds. And we see trajectories, and we're looking at 3 different trajectories here as they depend upon R naught, the reproduction number. And what you can see is that the peak happens, as we showed in that previous slide, the peak's going to happen where your susceptible population is 1 over R naught. And so, you know, for R naught really, really big, that is a small number. So that means that your peak doesn't happen until a large fraction of the population already have had the disease. Okay, so to avoid this, you need to have physical distancing to get R naught either less than 1 or relatively small, or to have a vaccine. Another option, of course, is to have excellent medical interventions that can slow morbidity and mortality, because that way you could have a sharp peak, but if everybody has a medicine, then they might not end up in the hospital or dead, right? They might just have cold symptoms. And there are plenty of people who are acquiring COVID-19 and only having cold symptoms and don't need to take any medicine. But there are others who are not so lucky with this. Okay, so here's another graphic that I'd like to show for SEIR. So this is kind of cool. What you can do is take your solution of the SEIR equations and you can rescale it. So there are a couple of rescalings we want to do here. The first one is to rescale time. So we have actually two time constants, but if we divide all of the equations by gamma, we actually get equations that depend only on one parameter, which is R naught. So that's the first thing we can do. So that allows us basically to rescale time to a dimensionless tau, which is gamma times t. So the second thing we can do is look at how these solutions depend on initial conditions. So it turns out that if you take an initial condition corresponding to what you would have in a pandemic, namely that you have a small infected population at time 0, some small number, and you have no recovereds at time 0, it turns out that the SEIR curves all collapse onto one curve, which is kind of cool, I think. So they collapse with one caveat, which is the time to peak infections. So the time to peak infections depends on your initial condition. And you might ask, how does that depend on the fraction of the population at time 0? Well, it depends logarithmically on that fraction, and you can see that in the insert. So here are some solutions of SEIR with very, very small initial infection percents, and you can see that there's just a time shift of all of them. They're not identical, I should say, so they're asymptotically collapsing. So they're not exactly the same solution, but they're very, very close. So that's another takeaway. So one thing that we can actually interpret this in a number of ways. One thing that we can do is we can ask ourselves, well, if we hadn't had controls, you know, we recently got a couple of studies out in California. And these are studies that were done on serology testing. So what they did was they tested some people in the LA County area and also up in Northern California. And what they found is that the fraction of the population that show to, at least from the ones tested, that we're looking at anywhere between say 2 and 4%, 4.5% of these counties are showing evidence of antibodies, which suggests that they've already had the infection. And that's a much higher fraction than the number of confirmed cases in either of these counties. So you might ask, how would that affect your SEIR curve? Well, what it does is it would change, if you wanted to start at some time, it would change the fraction of the population that's actually infected at a certain time. And you might wonder, well, does that change the size of the peak? Absolutely not. It doesn't change it at all. What it does is it shifts in time when the peak is going to happen. But what I should say now is that all of this is essentially irrelevant because we're under distancing controls. And so R naught has been brought way down under the distancing controls. So, so we're not in the apocalyptic case right now, which is good. Okay.
A quick question again,
Yeah.
like from Alberto and another couple other related ones. They want to know about R0 changing in time as long as some of these other parameters possibly changing in time, whether it's being assumed for simplicity, and if so, can you include the time varying nature of these parameters in more complicated models?
Yes, you can, and I have another slide on that coming up.
Okay, great.
Okay, is that it? Pretty much?
For
okay,
now.
Excellent. Okay, so this is basically a summary of what I just said, so I'm going to move on. Okay, great. So so one of the questions that I'd like to talk about is one of the things I'd like to talk about is what parts, now that we're under heavy controls, what parts of the population are actually getting infected? And we're seeing that the first responders, the people who are working in hospitals, nursing homes, the people who are out there, you know, working as law enforcement, the numbers we're seeing from them are much, much higher than the fraction of the general population acquiring this disease. So this is a statistic that I got from a news article, and this was a couple weeks ago. So at that point in time, they had over 1,000 NYPD officers in New York who had COVID-19. That department has 36,000 members. They had over 1,000 tested positive at that point in time, but they also had over 15% of the force who had called out sick, suggesting that maybe a lot more of them had that disease or some other disease. So we're seeing that the spread of COVID-19 through the population is preferentially going to people who have a lot of contacts. So, physical contacts with other people, as it should, compared to those of us who don't, who basically stay at home and stay with, 6 feet away from people whenever we go out of the house. So that's an interesting idea. And I'm going to get to that issue in a few more slides. So one thing you can do is you can take the SEIR model and you can look at it and ask, how can we use this model to understand the effect of distancing? So here's a plot that my team put together. This is a group of us who have a preprint out now on the archive. And we said, okay, let's measure R0 prior to the shutdown, or at least, within up to the early days of the shutdown. We did this for California. We used this particular calculation, used death data to estimate R0 to be about 2.7. By the way, the estimates for R0 are all over the place. So that's another issue, is the variability in the estimates. So take this with the appropriate understanding that this is not a ground truth. This is one estimate that one can get using a certain set of criteria. So we estimated R0 and gamma, and we took the initial I0 to be 0.1, and we just ran the epidemic using SEIR. And what you see for the uncontrolled case, which is not where we are, but you see for California that we would be expecting a peak coming up in a couple of weeks, and then of course the decay. And then you can play the game of, okay, now we're going to put controls in. And in our model here, we put the control in that R0 would be cut in half using distancing. And that's a gross generalization, but it's certainly consistent with the numbers that we're seeing coming out, in the last few weeks for California. Okay, so cutting R0 from 2.7 to half of that is still, it's bigger than 1, but it's still a relatively small number bigger than 1. So what you would expect to see is you would expect to see your numbers stay relatively flat. Then what we did was we said, okay, let's pick a date in the future. And by the way, this was before Los Angeles County came and said, we're going to have the shutdown at least until May 15th. But at that point in time, we said, let's remove the shutdown on May 5th. We picked May 5th because it's Cinco de Mayo, and that's a day people like to go out and celebrate in California. So we just picked that date somewhat randomly. And so you can see what happens if you take R0 immediately cut in half at early times and then bring it back to 2.7 on May 5th. You see that peak happens all over again. I mean, it hasn't happened because we've suppressed it, but the peak is going to happen almost identically to what it would have had, only just shifted in time, another month later. So that's what you get. So here's another fictitious scenario we can do with the New York data. So using the same methodology, we found R0 in New York to be 4.1. And so that peak would have happened already had we not had distancing measures in New York. But with an R0 of 4.1 and having it cut in half, what you would see is that you still would get a peak. It would just be a lot shorter. It would be fatter and shorter. It'd be flattening the curve, right? Which is something we hear about all the time. And you can see that you can see that it would start to level off, just a little bit into May. Now, if we decided in New York at that point to then remove the distancing and let people go out and lead their normal lives on May 5th, you would actually see an increase in cases, but nothing like what would have happened had we not had distancing measures early on. Okay, now why is that? That's because you have a lot of the population already infected. And we're looking for serology study results to come out of New York. I'm very interested. My group has taken bets on what those numbers are going to be, but we haven't seen them yet. So I'm not going to report here. on what that will be. But those are going to be very interesting numbers coming out of New York when we see those numbers. Okay, so I have a lot to talk about, so I think I'm going to skip this slide, and I'm going to move on to the next most complicated model, and this is perhaps one of the models that's most widely embraced by epidemiologists, and this is the SEIR model. So SEIR introduces another compartment. It's an exposed compartment. So instead of going straight from susceptible to infectious, you go from susceptible to exposed, meaning that you've been exposed to the disease, but it's sort of harboring in your body before you actually are able to transmit it to other people. And there's a lot of evidence to suggest that COVID-19 has this kind of behavior. So once you're exposed, you have a period of latency. And then from the exposed, you're going to move into the infectious case and start infecting people, and then you recover. So it introduces another time scale to your problem, which is this rate constant A in the E equation. It shows up, excuse me, in both the E equation and the I equation. But it's very similar to the SIR model. Another thing that you can verify with some simple calculus is that the behavior at the end of the epidemic for SEIR is identical to that of SIR. And the way that you see that is by simply taking the S equation and the R equation, dividing them by each other. We have that's exactly the same equation that we had for SIR. And that allows you to determine directly the end state of the disease. So that's another takeaway, that the long time dynamics of SIR and SEIR are identical. Okay, so now what I'm going to do is I'd like to shift to some data that people have studied already, and this is the 1918 pandemic. So that was the last time we had a worldwide epidemic that affected the entire world. And so this is a paper I really like. It's by Bootsma and Ferguson. Came out in PNAS in 2007. And what they do is they look at the SEIR model, and they look at how one might fit it to data from 1918. And so if you're going to look at the effect of controlling the population, you're really looking at reducing beta. And so they have two ways of reducing beta. One is with controls that are imposed by policy for, within a city or within a county or state. By the way, this is the US data that they looked at, okay? And so they have a transmission rate with the controls PC, but there's also a natural response of the population. So even if you don't have any controls at all, but you tell people that a certain number of folks have died, and this is a result of them coming into contact with others, people are naturally going to distance, okay? And so you can model that by looking at the mortality data and looking at a window of time prior to that point of time, computing the total number of deaths, and then looking at that as a way to also suppress beta. So that's the model that they used. Then what they did was they looked at a bunch of scenarios where they fit data to the different cities. And the scenarios involved fitting either to all of the cities as a lump sum, or fitting these parameters per the, individually for the data from each city. And they looked at a bunch of different models, and I see that when I changed my slides, that bar moved, so I need to fix that. So let me fix that. So this actually goes to 4. There we go. I switched the format of my slides, and some of my graphics moved around. So let's go back to that.
So while you change that, could I ask a quick
Yep.
question from Sinan Gunturk? He is asking, are there PDE models accounting for spatial transmission mechanisms?
Yeah, there certainly are, but we're not looking at them so much. I'll tell you why. Because there's a lot of evidence for this, and I think not that many people are looking directly at spatial models, but they are looking at network models. Okay, why would we care? Because when you look at when you look at what happened with the spread of COVID-19, a lot of the major events involve transmission of this disease from one area to another area by people traveling via plane, right? Or possibly by car over slightly shorter distances. So the early dynamics of COVID-19 throughout the world were really spread by dynamics that go way beyond just using nearby spatial contacts. They involve, we're living in a modern society where people travel using all sorts of methods of transportation. My personal opinion is that a network model is really important here. And that's also pretty true for the epidemiologist. I think if you want to look at spatial models, they're very relevant to populations that don't move like that. So that would be, say, animal populations in the wild, right? And possibly for very, very local spread of disease, like in a city. But even in cities, people are driving and taking public transportation and easily traveling from one end of the city to another. So human populations we just move with, we move way beyond our the length scale over which the disease is transmitted directly in space, right? So it's a really good question, excellent question. All right, so the model variant number 4 is the one that they decided was the best for this particular paper. And what they did was they looked, I love this paper, because what it does is it says, okay, here are 16 cities in the US, and we know what actually happened. We have the death data from those cities, and we also have information about the control measures. And so in each of these cities, the death data is shown by the blue X's. And so the control measures are shown as horizontal bars, and the x-axes are all time. Okay, so the horizontal bars show you the length of time and the location and time when these controls were implemented. And but they also show something very interesting. So the red curves show you the fit of the model with the controls to the actual death data, but those dark green curves show what they believe would have happened without the controls. And so I think that's really interesting. So, there's a beautiful case example from Philadelphia where they were seeing this virus start to spread through the population at early times, but they waited to impose the controls because they wanted to have a parade. So they had a parade, and everyone came to the parade, and they were tightly packed, and there was a lot of spread of the virus, and they had a big surge in infections, which is following the X's, and also the model fits very well to that. That's the red curve. And you can see that the controls were not imposed until they were well into this infection. And so it had only a modest effect here. Whereas some other cities that imposed the controls earlier, and by the way, the height of those bars, the height of the bars reflects how effective they believe the controls were. So you can look at some other cities where the controls were imposed earlier, and you can see that, like in Kansas City, for example, you can see that the worst case scenario, which didn't happen in dark green, is much, much higher than what actually happened. But they let the controls go before they actually got to a steady state case. They let them go fairly early, and you can see a second peak happened in that case. So these scenarios, I think, are very important for people to look at. I think people who are trying to come up with policy decisions on when to stop the distancing measures in their state or in their city need to be aware that this was done 100 years ago. And those cities that let those distancing measures stop a little too early did see another wave of infections. However, typically the second wave was not as strong as the first wave. So that's what happened in 1918. And that's an understanding using the SEIR model. Another thing that I want to make clear is that both of these models assume perfect mixing, and that's a huge assumption. And that's likely not the full story, and I have another slide on that. We have some questions? I see
There are a couple that we could ask. So there's a question about what the time scale is. Is the second wave related to the season at all in any of these graphs?
Yeah, these I believe are from the fall. So that's a good question. And I don't know that answer. We do know influenza has a known seasonal effect. And I think that's a good question. And I think that everyone's going to be watching the data over the summer in the Northern Hemisphere with COVID-19 to see, what happens. My expectation, personally living in California, is that California is going to be very careful with this, and we're probably going to see a slow burn for the foreseeable future. They're being quite cautious, and with good reason. So, for example, I saw the news briefing yesterday from the LA County Public Health, and they showed the graphs for the hospitalizations. One of the takeaways is that we're only at about half capacity in terms of beds, but when you get to the IC and ventilators, we have plenty of ventilators, but when you actually look at the ICU beds, we're already at about 60–70% capacity for ICU beds. So all it would take is a bit of a bump up, and we would suddenly hit the capacity for ICU beds in Los Angeles County. We are right now the epicenter of COVID-19 in California, Los Angeles County. So LA County is being very cautious with this and trying to stay ahead of it rather than having it take over the situation here.
And then
I have another question about different fractions of society. Could it be, or could it make sense to have to try to enforce different reproduction rates within different fractions, say with smaller risk, get more?
Sure, I'm gonna talk about that in a little bit. Okay. I really appreciate the question. Okay. All right, so let's move on. Yeah, okay, so I think this slide is a summary of what we just looked at, so I'm gonna go on. So we do have a preprint on the archive. And we looked at early time dynamics in the US for 3 models, SIR, SEIR, and the HAWKESN model, which I have not yet introduced, but I will in a minute. So our goal here, but none of us on this paper are epidemiologists. We did consult with an expert epidemiologist, and we also consulted with an expert in math biology. And so we decided to take an approach. By the way, let me just mention that a lot of the epidemic models, what the style of the research in that field is to have quite a lot of parameters and to use information from public health information, from record keeping about individuals who've acquired the disease, timescales that have been observed with from medical data. They have a lot of information that they're putting into these models. So we are not epidemiologists, we're not medical professionals, but we are people that look at data. And we decided that a different approach that one could use is to think about what is the most parsimonious model that one can think about for describing the data, and which of these parsimonious models are best depending on the kind of data that you look at. So this is a study that we did, and we looked at the early data, so just a little bit into the time period where we had distancing measures in the United States. So we looked at a few US states, and we looked at some countries for the exponential growth. And then we decided to use the Akeki information criteria to compare in terms of finding out which model might be the best fit to the data up through April 1st. Okay, so the one model I haven't introduced yet is the HAWKES process. Okay, so the HAWKES process is a point process model. It's a stochastic point process model. And it's a model that uses that assumes that there is some events that happened in earlier times that are going to influence future times. And that, of course, is very true in the case of an epidemic. So what we're doing is we're looking at the dynamic rate of events. We have a background rate of Poisson, that's a Poisson process. You could think of this, for example, within a state, the background rate is the rate at which people come into the state with the disease, okay? And of course, that could change too. Sorry, this is PowerPoint and my mouse, which, so I have one of those mice, you know, where you can touch it and do things and you can move it. And sometimes when you grab hold of it, it does two things at once. Okay, so what we see is that there's a background rate, and then the epidemic is captured by the second term here. What this is we have a dynamic reproduction number, R, that depends on time, and you look at R at the time of a past infection. You're summing over those past infections, multiplying that by a probability distribution that's also a time distribution, and we're using a Weibull distribution here. So, and those are the events, the past events. So the second term with the sum is capturing the process of an individual infecting another individual. That's what it's capturing. And more than one, because that's the reproduction number. It allows you to infect more than one person, and that's how you get an epidemic. Okay, so that's called the Hawkes process. My group has been working with Hawkes process models for almost 10 years. So we started working with them to understand the dynamics of crime in Los Angeles. And for those dynamics, you see clustering of events, but typically you're looking at reproduction numbers that are relatively small, less than one. For an epidemic, it's quite a different issue, but nevertheless, you can take a model like this, you can try to measure the dynamic reproduction number, and these calculations were done by George Moeller and Martin Short, who are on our paper. So for example, you can take the data from China and you can follow the dynamic reproduction number for China starting up around 3 in January, and then as they impose distance measures, you can see it decay to almost nothing. You can also look at data from countries in Europe, like we've got Italy shown in green, and the United States during its early times shown in blue. And then we also measured it for some of the US states, but we had very small data sets at that point in time to measure those quantities. So then what you can do is you can take these, by the way, I should add that there's a beautiful paper that came out in 2018. And what they do is their paper is, they call the model HAWKESN. So what you do is you take this sum here and you include a prefactor, which is the fraction of the population that's already been infected. And when you put that in there, you end up with a stochastic model that basically mimics SIR. And you can prove that it actually, that, you know, in the appropriate limit is exactly SIR. If you take the kernel W to be an exponential kernel, which is often used for Hawkes processes. However, for the epidemic, we wanted to take something that was more realistic, and so we used a Weibull distribution. But even with the Weibull distribution, if you follow this dynamic in time, you'll see a curve that's very much an SIR kind of curve. So it's very, very similar to an SIR model, but it's a stochastic model rather than a continuous differential equation. Okay, so what you can do, so here's the game you can play. You can take all 3 models and you can fit them to data. And we did this for 3 states in the US, California, Indiana, and New York. We had to do New York because everyone's looking at New York. And then we picked states where we live. So we have a couple of us in California and Georgia and Indiana. So we picked those states. And what you see when you fit the data, well, first of all, you see the R-naughts are all over the place, right? We got R-naughts all over the place. The Hawkes model is often finding an R-naught that's lower, but you can see why that is. So if we look at the graph on the right, what you see, and this is data from late March, so the SIR and the SEIR models are shown using the dashed line and the dotted lines. And those look like straight lines because that's basically your exponential growth at early time. Notice that the y-axis is the log of the count number. Okay, so since we're putting it on a log linear plot, exponential growth will show up as a straight line. Now the HAWKES model is computing a dynamic R0, and so those are the solid lines, and you'll see that those lines will change slope. And what you're seeing is that the slope is changing and it's flattening, even at the fairly early times, but this was after the distancing measures were put into place. So that's picking up the decrease in the R0. So we should expect that the R0 measured by the HAWKES is going to be less than, because of the distancing, and than the R0 measured by these other models. So that's what we get. Now using AIC, what you see is you can compare the models and pick the best model, and that's shown in blue. And what we see is that, so we're using two different data sets in the public domain. They're very simple data, the mortality data and the confirmed data. This is all from the Johns Hopkins website. Okay, so what we see is that the death data is very, very early time, because there's always a delay between acquiring the disease and dying. And that delay can be 2 weeks, right? So the death data is very, very limited data. So we're not surprised at all that SEIR, which has the smallest number of parameters, is the model that's chosen as the best model for the death data. Not a surprise to us. Keep in mind that the IKG information criteria penalizes against more parameters in the model. So for the confirmed case data, we're seeing the HAWKES process showing up for New York, and then we're seeing SEIR for the other 2 states. Okay, so that's the takeaway from this graph. But also the R0s are, there's a lot of different R0s showing up here. When you actually do the log likelihood and you look at in parameter space, so for SEIR it's pretty easy to do because there's not many parameters. So you can actually graph the results you're getting in parameter space and look at when you're trying to do likelihood estimation here, you can look at where the optimal value is. And what you see in parameter space is a fairly flat region, which is why you have, a larger spread here for the choice of R0. Okay, so I want to talk about other models that are floating around being used for forecasting. So this is one that's out of Spain, Alex Arenas group in Spain, and this is on the archive. And this model is actually based on models from a number of published papers. So I've listed a couple of the published papers up there. And this is a variant on SEIR. So they have susceptible, exposed, but they also have asymptomatic infectious. And that's important because we see that now in the numbers coming out for this disease. Then they have hospitalized, ICU, dead and recovered. Why would you want a model like this? A model like this is very important if you're trying to predict hospitalizations. And that's what most of the countries and states and county public health organizations need to know. They don't really care how many people are getting cold symptoms or asymptomatic, except that they are going to infect other people and possibly lead to other hospitalizations. So I'm gonna, since we don't have a lot of time, I'm gonna skip some of the details here and just say that what they did was they took this model and they looked at how it would fit to the different autonomous regions in Spain. And then using that information, they came up with some temporal evolution forecasts of the total number of ICU cases, predicting using a fraction of the isolated population from March 20th. So that's what they got. And they had that K0 as a variable for that particular model. Okay, so now what I want to do, I don't know how much time we have left.
I think it's up to you. You've been going about an hour now, so.
Okay, well, so I'm going to tell everyone, I'm going to keep on going, and so people who need to go can go. But for this particular seminar, given that it's a data science machine learning group, I wanted to talk about one measure that I think is important to look at. And this ties into topics like L1 compressed sensing, which I think is of interest to some people who are going to be visiting, this particular One World seminar. So I want to talk about network modularity. So network modularity is something that's been, so I mentioned earlier that networks are important. So when people look at early time dynamics of epidemics, one of the things that they like to look at are contact information about who contacts who and who might be spreading the disease. They'll write down what are called contact matrices, okay? And so that's some kind of epidemiology lingo for the network for the spread of the disease. So when you look at networks, there are a lot of different statistics that you can measure as far as networks are concerned. And one of the things that is popular for people who study network science is measuring communities and how much does the network lend itself to being described by sort of communities that interact strongly with each other and not as much with other communities, right? So one way to measure that is using something called modularity. This is probably the most popular method, very widely studied, thousands of papers on Google that have cited the original Newman-Jervan paper. So what they do is you take a network. So a network is basically nodes and then edges between nodes. And so for a contact network, you would assume that the edges are either 0 or 1 with weights 0 or 1, but you can put weights between 0 and 1 as well. And so that's commonly done for other kinds of graphs. And for the machine learning community, one type of graph that many people know of are similarity graphs for big data, right? So one can also apply these ideas to big data as well. Okay, so what you do is you have to come up with a null model, and the Newman-Jervan null model assigns an expected edge weight between nodes Ni and Nj to be Ki Kj over 2m, where Ki is the degree of the node, which is just a fancy way of saying the sum of all the weights coming into that node. If you sum up all of the degrees for the whole network, you get 2m. And so that gives you the total edge weight of the graph. And so these are undirected graphs. And so then to do modularity, so for modularity, what we do is we consider a partition of the graph. So you imagine that the graph is now cut up into a number of groups. And so then you have, the groups are denoted by G. And so then that partition has something called a modularity. And so the formula is in 2.1, which is taken from their paper. So gamma is a parameter. That's the resolution parameter. And then the term delta GI/GJ is 1 if GI is equal to, if the two groups are the same, and it's 0 otherwise. So this is a formula for the modularity. And so for modularity optimization, you're trying to maximize this formula to figure out what the natural communities are in the network. Okay, so here's a paper on epidemics in networks using the SEIR model, but for a network, and looking at the role of modularity. And I think it's a really interesting paper, and it's something that we should be looking at. So this came out in PLOS Comp Bio in 2010, and they use the SEIR model. So what they do is they construct in this particular graph, they're looking at synthetic networks where they can play with the modularity, and they can create these networks with different modularities. And they look at some of the statistics, like the peak prevalence of the disease, the final size, the duration in days. And what you see is that and then modularity is shown on the x-axis. So larger modularity means a more well-defined community structure. And you can see as the modularity goes all the way to 1 that these numbers for final size and peak prevalence really decay quite a lot. And the colors represent different values of R0. So we have R0 2.5, R0 of 3, and R0 of 4. So So I thought that was interesting, but even more interesting, and that we can think about this in terms of distancing. And I don't know to what extent this is actually describing distancing, but it's a question that I want to pose. So we can look at, and this is from the Salathe and Jones paper. You can look at two different examples. This is for a network that has a medium modularity score and one that has a high modularity score. And you can look at SEIR running through the network in time. And so what we see for the medium modularity score is this graph and shown in A, right? And so you see over time that you have a rapid increase up to a peak and then a decrease, very much like your infected curve in SEIR, okay? But if we take the same disease and we put it on a network that has a strong modularity score, you see something completely different. What you see is something that looks more like, and this is an opinion of one here, it looks more like the controlled burn that we're seeing right now under social distancing, right? So what you see is that there are sort of little bumps, but and it doesn't look like a curve at all. It looks kind of like, you know, groups of people getting sick over time, but very much the controlled burn kind of scenario. So I found that really interesting, and it's something that I'd like to look at more. One thing that I can say for people who are coming from compressed sensing is that modularity has a direct connection to compressed sensing. So I wanted to share some of that with you. And that was work that we did in our group about 8 years ago, starting about 8 years ago, in collaboration with Mason Porter, who was at Oxford at the time, but is now at UCLA. So at the time I was working on developing methods for fast methods for solving penalized graph cut problems for machine learning. And I mentioned this to Mason, and Mason said, you ought to try some of those on modularity. So we thought, okay, let's try that. So what we did was we took this modularity function and we were able to rewrite it, I mean, not approximately, but exactly as an L1 compressed sensing problem, which is kind of fun. It's not that hard to do. So what you have to do is you have to write down some formulas first. So the first formula, the most important one, is you can think about your group assignment as basically taking a function and assigning the function to nodes. And that function is basically going to assign a different value to nodes in the different groups, right? So if f is that function, we can write down the total variation of f on the graph, and it's just the sum over, my crazy mouse again. It's just the sum over all I and j of the weights wij times the absolute value of the difference between f evaluated at I and f evaluated at j. So let me put that in words. If the two nodes are in the same group, then f is going to have the same value on those nodes, so the difference is 0, so you don't count that edge. But if the two nodes are in different groups, then the absolute value will be different and you'll count that edge. So that's what we're measuring. So that is actually exactly the size of the cut if we're thinking about this in terms of graph cuts, right? So if you define a partition of a graph and you want to measure the size of the cut, that is the total variation of this function. Okay, we can also define a weighted L2 norm of the function where we're including the degree of the node in this sum. And then we can also measure a mean, a weighted mean for that function. So if you use all of those things, what you can do, and I'm going to cut to the chase here and just tell you the answer. So what you have to do for modularity to connect these two things is you have to fix the number of classes, but then of course you can optimize over the number of classes. So for example, if we take two classes and we just look at a cut into two classes, then maximizing the modularity is equivalent to minimizing this functional here, the total variation of f minus this quantity here, which is like a second moment with the weight, with those weighted quantities, right? Then what you can do is you can easily generalize this to n classes, and it's the same formula exactly. So what you see is that maximizing modularity, if you want to find the optimal partition, it's equivalent to solving these penalize minimum TB problems, but then minimizing also over the total number of groups, right? So it's a pretty complicated problem to solve, but if you happen to have something that has natural communities built into it, some of the compressed sensing methods can work really well. So the one that we like is the MBO scheme, which came out of my group, but comes from even earlier work in PDEs and the continuum by Merriman, Benson, Osher. That's why it has those initials. Okay, and then more recently, one of my former students, Zach Boyd, did his thesis on improving this idea of using compressed sensing methods for solving modularity optimization problems. So he came up with formulas that are even more kind of convex, have a more of a convex structure, which gives you even faster and more efficient algorithms. So his balanced TV formulas are also shown to be equivalent for this modularity problem. And this is the shown on the bottom is an example with hyperspectral long-wave infrared data. It's an image processing problem trying to find the natural groups of pixels in the image. This is a plume moving across a scene in the desert. So I'll finish by just mentioning that last year in the Journal of Nonlinear Science, also with Mason Porter, we looked at a special class of stochastic block models, the planted partition model. And Newman has some relatively recent work on that, showing that modularity optimization for the planted partition model is equivalent to a maximum likelihood estimation for stochastic block models. And there's a formula for that. And what we were able to do is to show that this actually is a discrete analog of a beautiful continuum problem in surface tension that was with an algorithm that was developed by Esadoglu and Otto not so long ago. So it allows us to take ideas from continuum free boundary problems and use them to solve these optimization problems. So none of these things are directly applied to epidemics, but I think it would be interesting to look more carefully at network modularity and how that's going to affect the spread of COVID-19, and what can we say about the current network structure under social distancing versus what we had prior to that. So I think I'm going to stop with that slide. And
okay, sounds great. Thanks a lot for agreeing to speak. It was excellent. I'm going to stop the recording.